Welcome back. In this video, we're going to begin to talk about data types. Data types are very fundamental to programming because we need to understand how much memory we're using, how things are stored. These are some of the really good, important fundamentals to any programming language. And data type storage can vary, and the terminology for each type can vary by language. So for this video, we're going to talk about them at a very high level. We're not going to go too far into the weeds. We're going to kind of introduce them. And then as we go into each language, we will talk about what that language uses for things like floating point and integers and things of that nature. So again, this is going to be a very introduction to a very high level introduction to data points, and let's just kick it off and start rolling. Booleans. We've talked about Booleans in the last videos, and Boolean expressions are either true or false, right? Now we know that technically any non-zero value is considered Boolean true, but we're going to use 1 for our convention and 0 for false. Now you really only need a single bit for that, right? But rarely in computer languages do they only give you 1 bit. Now, to be honest, in some of the newer languages, like C# now has these bytes that you can set up where each bit is a flag, and that's some pretty cool efficiency that you can get where you can only use 1 bit for a flag, but they're still giving you a byte worth of flags. So using 1 bit is not efficient because of the speed and the way the processors work today. So the next data type is a char, okay? A character. A character is either ASCII, extended ASCII, or Unicode. Most modern languages are using Unicode these days, but for C, since we're going back to one of the first languages really written that is still actively used today, because it's the root of C++, it's the root of C#, it's the root of Java, they pretty much started out with ASCII, and that's 7 bits. So we're going to use a byte, but the 8-bit will be 0. And like I said, now the newer versions of C do allow Unicode, obviously. The language itself has evolved. We're going to fundamentally stick with ASCII, where a capital G is 1000111, and the leading 0 is assumed because we're in ASCII. And you can download an ASCII table and take a look at it. Okay? We've talked about ASCII, we've talked about how these are represented in the intro course, but basically the ASCII value can be stored as an integer, or it can be interpreted as the actual character that it represents. Now let's talk about integers. Integers are whole numbers. There's no fractional part to an integer, it's a whole number. All right? And basically these whole numbers can either be signed or unsigned. Now, I'm not going to drive too far into the weeds. I am going to show you that if it's a signed integer, you get from -2 to the n minus 1 through 2 to the n minus 1 minus 1, because one of the bits has to be used for the sign. If it's unsigned, you can squeak a little bit. You get another power of 2 out of it based on how many bits you have, because you lost the sign. So you can only do 0 through whatever. So if you're using a single byte, you get 0 through 255, which we've seen. You don't get, but 2 to the 8th is 256, but you have that -1 because the 0 gets a vote, right? So in signed, the plus or minus basically gets a vote and takes up some of the room. Here, 0 actually, and this also includes 0, by the way, but 0 gets a vote for this as well. So 0 to 255, for example, is 1 byte. All right. So these are the most common terms. You can hear quad words for long longs, but basically, let me show you how many bits are in these. So you've got 4 bits in a nibble, 8 bits in a byte. Say that right. 16 bits in a word. A long gets 32. A long, that's actually a thing, is 64. Like I said, sometimes that's called a quad word. And then octaword is sometimes called a double quad, but basically that's 128. And there you have it. Okay, that's integers. And for floats, I've got a couple bullets I'm going to show you here in a minute, but I want to really kind of focus on what I want you to know about floating points. And it's really simple. I want you to know the basics of how they're stored. And that is, they take the significant digits times the base and the exponent. So if I'm going to do 23.456, that's the number I want to store. I'm going to find all the significant digits, which is 2, 3, 4, 5, 6, 7. And that is going to be called the significand. Okay? Times 10, because I'm in base 10, is a decimal number, to the minus fourth, which means I'm going to roll the decimal over here. And this is how I'm going to store it in memory. Okay? That's all I want you to know. You could look up 8 pages on Wikipedia alone on how this is done if you really need some help going to sleep some night. Okay? There's a lot of math behind this, how it's stored, the benefits of doing it different ways. You can look that up. It's way outside the scope of this course. There's probably a couple of you, though, that are just going to run to Wikipedia right away and see what I'm saying. That's fine. It's all out there, okay? But what I want you to know for this course, for Advanced Computer Science Principles, is it's the significand, the base, and the exponent. That's how it's stored, okay? So the other thing I want you to know is that these are high precision fractional numbers. Notice what I did not say. I did not say that they were real numbers. And the reason I didn't say that is some real numbers have infinite decimals. They just keep going on. If I point, look at pi, right? It just keeps going. There's no end to it. Well, I'm going to run out of bits somewhere. So it is not accurate to say that these are the real numbers. Integers are whole numbers. But again, even whole numbers can imply, I'm not talking about the infinity of aleph null here. I'm talking about integers as high as I have bits for. Well, precision numbers, whether it's a really small number or a really large number, it is also for the number of bits that I have to represent it. So they are approximation to reals, but they are not the real numbers. All right, and the other one is, like I said before, we use them for very small and very large numbers. Okay. Now, the next ones we're going to talk about, I'm only going to kind of dance on the heads of them because they're what we call composites. Okay, and they include arrays, strings, enums, structs, and classes. And we're going to define these as we go through the languages of these courses, of this course and the next course. So I'm not really going to get into the definitions of these other than to say that when you get into structs in C and classes in C++ and Java and C#, you really begin to build your own data types, custom data types, which is really cool. And when you get good at it, it's a lot of fun. Other data types that are not implementations that use multiple versions of built-in data types include what we call traditionally data structures. Okay? Hashes, tables, linked lists, double linked lists, trees, binary trees, tries, different thing. Okay? All of those are composite data types or data structures. Okay? And what they have in common is we know that primitives are built in, and we know that these are made up of more than one primitive. Okay? And that's all I really want to talk about for this for now. Okay? And I want to jump very briefly to one more type of data type, and those are called memory pointers. Now, memory pointers are storage of a memory address. So if I have a memory pointer to the variable y, if I store a pointer to y, I'm storing the memory address of where the value of y is located. And when we get into the language C, we'll do a video on pointers, okay? And we'll show you some code involving pointers, okay? Pointers are extremely confusing at first, but if you hear about them enough, it begins to sink in, okay? We can control pointers in C and C++. After that, modern languages have abstracted away pointers from us, okay? One of the big reasons is hackers. If I want to run your heap and your stack together and take control of your instruction pointer and steal control of your computer, to do this efficiently, I need access to memory pointers. I need to be able to move pointers in memory around at my will, okay? So modern languages use what's called managed code. I no longer have to allocate memory or deallocate memory as I need it. All of that memory allocation is handled for me, and when variables go out of scope, they are garbage collected. And unfortunately, in most languages, I don't get to control the garbage collection, which is a security flaw that comes with abstracting away pointers. But it also makes my life as a programmer a lot easier. So, harder to hack, easier to write good code that is less vulnerable to hacking if you do it correctly. So, while we're in C for this course, we're going to talk briefly about pointers. We're not going to go into them a lot because we don't need them for what we're trying to teach in this course, but we're going to kind of show them a little bit. We'll do some light pointer work, and beyond that, we'll be done. Because when you get into CSA, you're getting into managed code anyway, and we're more concerned with teaching object-oriented code and getting into some design structures like MVC programming paradigms. So for this course in C, we'll touch on it, and even the last half of this course we do Python, we're not going to touch pointers, okay? So what is coming up next? Well, actually, let's finish the slide here. We know primitives are built in. We can control pointers, like I said, in C and C++. And again, like I've been saying, once we move to modern languages, it's all managed code. We're not going to control the pointers. But pointers are a primitive, and they are a reference to a memory location. Okay? That's all it is. All right? So, what's coming up next? We're going to talk about constants and variables. And this is probably one of the few remaining videos before I kick you over to the language C series that I'm producing for the rest of this fall semester in this course. So I will see you on the other side.